Again, today we want to look at diffusion in a tube with the change in path length. Diffusion in a tube with change in path length. So if we look at unimolecular diffusion problem that we were looking at previously, we will see that diffusion in a tube with a change in path length, it's more or less like an extension of that problem. So as indicated there, you find that so let's look at an example as indicated there. Then so this is diffusion of benzene in a narrow tube is occurring, but is that is happening at a given time t, the level z, the level is zm from the top. So as diffusion proceeds, the level drops slowly. So we are saying we are somewhere there at a level z, there, and as diffusion proceeds, the level is the level is dropping, and as the level is dropping, it means the length in which the benzene molecules are going to move to get out of this tube is also changing. Right. So we want now to derive the equation for the time TF, for the level to drop from a starting point Z naught there, from a starting point Z naught at time T naught to a point ZF, which is at time T equals to TF. So for us to be able to derive, let's assume uh, a pseudo steady state conditions, since the level drops very slowly. Let's assume pseudo steady state conditions since the level drops very slowly. So as time progresses, the path length Z increases. So you would find that we will have to use the equation that we derived when we were looking for molar flux for unimolecular diffusion, since all other conditions really the same. So at any time t, you'd find that this equation, at any time t, this equation there, which I'm pointing at, this equation holds, but the path length z is z, and this equation becomes equation 1.3, the becomes this equation below there, and you would find that NA and Z are now variables, no longer constants. So NA and Z are now um, variables. So if we need to solve that, um, let's assume a cross-sectional area of A, which is 1 square meter, and the level drops GZM in dt seconds. And our density being assumed constant is rho Al and the molecular mass Ma. So the kg mole of A that have left and diffused is. So the kg mole that have left and diffused Na So as we saw previously there, we said that Na is equal to capital Na, which is the molar flux times the area A. Now I want to look at how do we calculate this. Right. For us to be able to do that, remember we said this is happening in uh in a tube. Right. So for us to know moles that are living is we just determine the volume times the density. So this change in volume times the density will give us mass. So that mass divided by mr give us the number of moles that have left per over the time duration. Over the time duration there. So our volume is our surface area. Our volume is given by surface area times change in path dz. Then our density is rho over ma dt is indicated there, right? So this equation, this this is giving us number of moles. Let me go back again on that one. This is giving us number of moles that are living per time. And that is exactly equal to this equation, Na is equal to capital NaA. And as remembering that, we assumed that we've got a surface area of 1, then Na times 1 is equals to rho 1 dz over ma dt. So now we need to integrate this equation. We need to integrate this equation using the limit t equals to 0 to tf, and from z equal to z equals to tf is indicated there, where we've made use of the limits. But before we integrate, we need to make sure that we substitute for Na, then we make gt the subject of the formula. Then we can now integrate. So integration of this will give us TF is equal to rho YB log mean over C GAB MA YA minus YA2 ZTF squared minus ZTF squared over 2. Right. Um, so let's now, to avoid any confusion, where you would want to understand where A1 and why A2 is come from, it's a matter of you now replacing your PA1 and PA2. You convert that to more fractions, is indicated there. So the method shown in this illustration has been used to determine diffusivity GAB, and in this experiment the starting path length Z naught is measured at t equals to 0, and also the final ZT at TF. Then that equation is then used to calculate GAB as indicated there. So this same equation can be written in terms of partial pressure to give equation 1.322 as indicated there.